This video series presents an integrated simulation workflow for antenna design, coupling, and installed antenna performance in ANSYS HFSS, SBR+, and ANSYS EMIT. We'll solve diverse electromagnetic problems involving antennas, primarily on an automobile. These problems include electrically small, moderate, and large structures. In part 1, I'll describe the workflow, different electronic solvers, and an automatic adaptive mesh refinement feature in HFSS. Our workflow includes various steps from initiation to completion. Generally, an antenna is designed under the assumption that it sits in free space or on an infinite or well-defined local finite ground plane. Therefore, first we'll select an antenna from the number of known topologies present in the HFSS Antenna Design Toolkit. In reality, antennas readily couple to their local environment, so we'll place our antenna within a standalone side view mirror of a car and create a 3D component. We'll add this 3D component to the car body and study the effects of scattering by the car body. Next, we'll import additional antenna models into the car and perform antenna-to-antenna coupling analysis. At this stage, we'll extend our analysis to a realistic scenario wherein the antenna on the car communicates with a home Wi-Fi system. Antenna-to-antenna coupling can lead to interference between onboard RF systems. These issues can be predicted and mitigated by ANSYS EMIT. So in the final step of our workflow, we'll model RF interference between RF systems on the car. This phenomenon is often known as RF co-site interference or co-site RFI. We'll execute the complete workflow using ANSYS Electronics Desktop, which lets us explore ANSYS HFSS and SBR+ and provides a data link to ANSYS EMIT. Depending upon the geometry, material complexity, and the electrical size of the problem, you can accordingly leverage the strength of multiple solvers in ANSYS Electronics Desktop. For instance, finite element methods, or FEM, can handle geometries of arbitrary shape and high degree of material complexities efficiently. In this method, the model is divided into tetrahedral elements conformal to all surfaces of the geometry. The model is represented with a volumetric mesh and solved to produce field solutions. The integral equation solver can be used to efficiently solve antennas in an open environment or electrically large metallic structures. Typical applications include radar cross-section, co-site analysis, and antenna placement. For instance, an antenna mounted on an automobile or an aircraft. Additionally, a hybrid finite element integral equation solution leverages the advantage of both simulation techniques to most efficiently solve electrically large problems. For electrically large problems with structures hundreds of wavelengths in size, you can turn to a class of field solvers that employ asymptotic techniques. In this approach, an advanced shooting and bouncing ray solver, known as SBR+, uses a ray tracing technique to generate surface currents on the antenna platform for metals and dielectrics. SBR+ is also suitable for rapidly solving electrically enormous structures involving thousands of wavelengths in size. You can model transmissions and reflections in very large structures like vehicles, aircraft, radome, etc. Advanced SBR+ also employs creeping wave physics and generates accurate solutions for antennae mounted directly on curved structures. These simulation techniques can be accelerated using high-performance computing, also known as HPC. HPC enables higher fidelity, accuracy, and speed to simulations, enabling parallel processing for solutions of the toughest and most challenging models with greater geometric detail, larger systems, and more complex physics. Before using these simulation technologies, you need a mesh to represent your model. Fortunately, HFSS offers an automatic adaptive mesh refinement technique that lets you focus on your design instead of spending time in determining and creating the best mesh. To set up your design, import or create the geometry, and specify materials, boundaries, excitations, and frequency. To illustrate, stages of the adaptive mesh refinement for a bow tie antenna from the initial mesh through the final mesh are shown. The mesh elements are refined in areas where strong electromagnetic fields exist and/or the field gradients are high. The mesh is coarser in the remaining areas. This process makes the mesh accurate and suitable for efficient simulations, leading to highly accurate solutions. The plot shows the two arms of the bow tie antenna illuminated by electromagnetic fields. This meshing technique is enhanced by multi-frequency or broadband adaptive meshing, which adapts the mesh at multiple frequency points, yielding greater accuracy across a broad frequency range. This conical sinuous spiral antenna shows the return loss for multi-frequency solution at 4 GHz and 10 GHz. This concludes part 1. In the next part, we'll start with our workflow.